The unit step function. You've probably seen the unit step function before. Sometimes it's called the Heaviside function. It exists in both continuous time and in discrete time. In both cases, we use the letter U to represent it, U for the unit step. In discrete time, our independent variable is n, and n takes on integer values from minus infinity to plus infinity. U of n, unit step function in discrete time, is defined to be 1 when n is greater than or equal to 0, and 0 when n is less than 0. Picture of it is as you see here. When n is 0 or larger, it takes on values of 1. When n is smaller than 0, it takes on values of 0. N is a discrete variable, so it only occurs at discrete. N is a discrete variable, so it only occurs at discrete units of time. The continuous case is defined equivalently using U to represent unit step. Our independent variable is now t, which is a continuous variable. It still takes on an amplitude of 1 when t is greater than or equal to 0, and an amplitude of 0 when t is less than 0. In this case, it's a continuous variable, so it's 0 for all these t less than 0, and it's 1 for all these t greater than or equal to 0. As with other functions, we can shift its location. If we put in an argument of t minus 2, using our knowledge of functions, whenever the argument changes, we change it everywhere else in our equation. This is then equivalent to this other form here. So when we have u of t minus 2, our unit step function turns on at time t equals 2. Quite often, you will see the difference of two unit step functions. U of t starts at time 0. U of t minus 2 starts at time 2. If we look at that, at time less than 0, we have a 0 subtract 0. At time between 0 and 2, we have a 1 subtract 0. And for time greater than 2, we have a 1 subtract 1. So we have a 0, a 1, and then a 0. This is what we use to get a rectangular pulse, a function that turns on at some time and off at some other time. It's possible to add unit step functions, in which case we've got 0 plus 0, 1 plus 0, 1 plus 1. This does not have as many practical applications, but you need to know that it's possible to do this as well. Quite commonly, you will see a unit step function multiplied by some other function. For example, we can take our unit step function and multiply it by an exponential, e to the negative t. E to the negative t is a decreasing exponential that looks like this. Our u of t, because it's just t and not t minus 0, starts at time 0. When we take the product of them, we then have a 0 times our function when we're time less than 0. And when we're time greater than 0, we have a 1 times our function. 0 times anything is 0. 1 times anything is anything. So we wind up with a 0 and then our function. This is the method we use to turn a function on at some given time. It's also quite common to see some arbitrary function multiplied by the difference of two unit step functions. Another example, that same decreasing exponential multiplied by a difference at time t and t minus 2. There's our decreasing exponential. There's our difference of two unit step functions. We take the product of them, 0 times our function, 1 times our function between 0 and 2, and 0 times our function for t greater than 2. 0 times anything is 0, 1 times anything is anything, 0 times anything is 0. So we wind up with 0, our function, and 0. This is the way we use to limit in time when our function is on. There are many other things you'll see with the unit step during this course. I hope this has provided you a good review. Practice these. There's some quiz material on Blackboard.